Let's get started. It's my great honor today to introduce Professor Zhi-Xun Shen from Stanford University. Zhi-Xun got his bachelor degree from Fudan University in China and his PhD from Stanford. I did turn on the mic. Yeah, okay. Yeah, so Zhi-Xun got his bachelor degree from Fudan University in China and his PhD from Stanford University. Zhi-Xun is a world leader in applying angle-resolved photo emission to study quantum materials. In the past 4 decades, he has been at the forefront in transforming angle-resolved photo emission into a precision spectroscopy. He has many groundbreaking works. Among them is the observation of gap nodes in the copper oxide high temperature superconductor. And that result was followed by phase sensitive measurement, which now solidify the consensus that the Cooper pair wave function in that material has D-wave symmetry. For that achievement and many others, Zhi-Xun was awarded the 2011 Barclay Prize of the American Physical Society and was elected to the National Academy of Science. Today, we are privileged to have Zhi-Xun here to tell us his journey and also tell us the open problems lying ahead, which continue to excite this exciting field. Would you please join me in welcoming Professor Shen?
Good afternoon. It's really a great privilege to come here to Berkeley and to share with you some of the thoughts and the results we find on this great unsolved problem in physics, namely the origin of high temperature superconductivity. Every time I come here, I learn so much from people and colleagues here. And as you will see, that a lot of my own work was also done here in the Hill, but also at the SSIL. So what I want to hope to sort of accomplish will be separate this talk in 2 components. There's a component to tell you the things we feel we have confidence. So I at least hope to convince you the credibility of this experimental technique. Then the second component is more speculative, but it's where I'm thinking the field is. Okay. Let me start by acknowledging collaborators. What I'm going to tell you today is a journey. So it involved a lot of collaboration, and this really is a team we've been working together a lot, involving people at SLAC and also ALS, and also University of Tokyo. So this is sort of long-term collaboration. And I will specifically acknowledge the students of the specific work when they come up. And over the years, also we collaborated with sample growers, both locally and internationally. And it's just such a joy to work with Deng Hai and many other series collaborators on this project. Okay, let me start out a slide all you know. That's the discovery of the Cuprates. And as you can see that when it's about 70 years of sort of failed attempt to bring up high temperature superconductivity. And at the time, when I was a graduate student, everybody thinks that that's the limit, and that there's very little hope. Then suddenly, a discovery by Mueller and Bernard changed this landscape. As you can see, this go up dramatically. And it's timely that recently, under high pressure, actually we have another family of nickel-based superconductor also has a transition temperature above the liquid nitrogen. So actually, the leader of that group actually did a postdoc with Bob here at Berkeley. Okay, so then the question, well, what is the origin of that? That's always a very interesting and debated issue. But a bit of history, it turns out that's the Nobel lecture from Bednorz and Mueller. It turns out they actually searched for high temperature superconductivity in the nickelates first. And after 2 years, didn't work, and moved on to the cuprate and made that discovery. Their vision of searching was the following. Those are oxides, that means extremely poorly screened systems. And because of the poor screening, the electron-photon coupling will be very strong. In particular, in their case, is the Young-Taylor distortion mode. That is their reason, believe this system might harbor high-temperature superconductivity. That started their search, okay? So this, of course, is the same perovskite system. From the very beginning, there is an issue, and there are many ways to present that challenge to this line of thinking. Probably the best one was sort of subscribed by Bert Matthias. And he basically said, you look for best superconductors right before they go to hell, okay? In that vision, essentially to say that you can always crank up, as Mueller and Bednorz thinking about, crank up the coupling constant until you reach a point the material itself becomes unstable. That's what he means by goes to hell. In other words, how you can achieve the strong coupling without structural instability. So that is always an issue. And immediately, there's another vision that's represented by Phil Anderson. And you can see the cuprate was discovered in 86. And in this 87 paper, and he basically said the cuprate problem goes beyond superconductivity. It's really the continuation of the oxide insulator problem. We have theory works very, very well for the silicon class of material, okay? But that fails poorly in those oxides. So in his vision, then the physics of this system should be described as emerging from this so-called doped Mach insulator. In particular, he's proposed that this Hubbard model, which is one step beyond the non-interacting system by explicitly considering the cooling interaction on site. And there's this emerging self-generated exchange interaction that can give you the pairing interaction. So that's how the field, you can see, has two very different visions for the problem. And for a while, okay, often you hear high TC talk, and people talk about Hubbard model. That's coming from this vision. For a while, you kind of forget the difference between a real material superconductivity and the Hubbard model description. So what I'm going to talk about is hope to give you a sense that basically I'll try to describe the progress made and from the perspective of particular experimental technique. Then I'll talk about the remaining puzzles. Then I'll try to address what is the essential ingredients of that. Then I'll try to benchmark this particular vision from the Hubbard model. Is that sufficient? And finally, I'll speculate a little bit what likely is what happened to this question. You look for superconductors before they go to hell. Okay, so this is the technique. It's a photoelectric effect. You shine the photon and you generate electrons and you detect those electrons. And the modern spectrometer is really mostly a hemisphere. As you know, hemisphere is a fabulous imaging machine. That means that anything you detect on the detector can be traced back. Therefore, you get both the trajectory means angle of those electrons as well as the energy of this, because only if you put a positive bias on the middle and negative bias on outside, only the electrons with the right amount of energy can pass. And that's how you get energy and momentum relationship and dispersion relation. So formally, if you have a non-interaction system, and that's the spectrometer, you get a sort of delta function. But in an interacting system, then you could see the complex line shape. And from that, you learn things about the interaction. And the line shape in the condensed matter physics is often described by so-called self-energy. Imaginary part and a real part. These tell you the lifetime of the quasi-particle. The real part tells you the mass. Okay, this technique has been, applied to a lot of problems, and that's where the D wave was discovered. And you can see there's a lot of things being applied, and also including the topological insulators. So this is the cartoon version. Basically, the physics is more or less described by a single layer, and you have a reservoir layer to dope the system. And you can dope them with both holes and electrons. If you dope them with holes, then you have a larger superconducting dome. And that's where most of the research will be. And if you dope it with electron, you have a smaller one. And you can see this long-range magnetic ordered insulating state persists into a much larger region in this one. So if you do a Fermi surface band structure calculation, then you have something look like this. You have a single band, and you have a large Fermi surface. And going forward, when I say node, that means 45-degree direction. When I say antinode, means Brownian zone boundary. So that will be the notation of this. Okay. Now, we know we have an unconventional superconductor. So you can ask, what is an unconventional superconductor? There are many criteria. You can have a sign change. Cooper pair is not the spin singlet. You have non-zero center of mass momentum. And there's also disconnect between period and TC. So if you put all these together, there are actually a lot of unconventional superconductors. Okay. Now let me talk about this aspect. And it turns out in the cuprates, really there are two things which is unusual in the superconducting state. One is the D-wave pairing. And of course, these two are given once you have that. Okay. Then there's a disconnect between pairing temperature and TC. Those are the things after this year's work, and we have more or less of a consensus. Now, let me try to show you. As Dong Hai pointed out, that almost 3 decades ago, we measured the system, in particular along the B direction. That's, as I said, no direction. You see the spectra above and below TC are almost identical, 2 different temperatures. And we said it looks like what you would have expected of D-wave node is gapless. On the other hand, if you go to the antinode, there's a clear difference between spectra below and above TC. And at that time, that's the best we can do, taking 4 spectra with this kind of resolution. Within the range, sample surface is still clean. Of course, with time, this improves. And later on, the efficiency of the experiment is such that you can map the entire Brownian zone. And then you can take the spectra along the underlying Fermi surface, as we talked about it, and you see the spectra shift. If you will plot the peak position of this one in momentum space, it looks like this, that's the data, and the green curve is that of a D-wave functional form. So this is very consistent with D-wave, and these are the people who taking those spectra, that's Bogdanov, Yulin Chen, and Xinjiang Zhou, then when they were working together of taking those data. Then another 10 years later, that was the thesis work in Avishek. And we said, if this is a D wave, let's see what the D wave superconducting gap will evolve as a function of doping. Okay. And to measure the D wave gap, the most precise one is this linear slope of the node. Okay. And so that in her thesis, what she finds is very surprising was that the superconducting gap does not seem to have any connection with TC. You can see this slope is identical when for sample with TC of 40 Kelvin to 92 Kelvin. So this sort of first hint there is a disconnect between TC. In other words, the superconducting transition temperature in those doping range were not controlled by the pairing strength or the D wave gap node. Okay, certainly here in this range. So that's a hint of possibly the superconducting pairing above the gap. Okay, so this is one thing you see things, you don't see the things you expect to see. But it gets worse. You see things it shouldn't have been happening. In other words, that is the thesis work on Lai Fang's thesis. And what you find is that if you plot in this doping range, okay, if the spectral weight of the photon emission at the anti-node and plot the intensity, you find really interesting correlation between the rise of TC and the rise of the intensity. And back then, it turns off at 19%. We didn't quite sort of appreciate this one. Empirically, what is surprising to see, this one appear to be correlate with the superfree density seen in conductivity. This is not something you would have expected. Okay? So it does the things you don't expect it to do. So this, again, is hinting that there's a disconnect between the pairing gap and TC. Now, in you can also visualize this in the following way. Here I'm showing you the spectra taken at the anti-node. Okay? And as a function of temperature, you can see that as I go towards the TC, which is this curve, the gap certainly does not close. Okay? And it actually closes at a higher temperature. Okay? And you can see that we know this is the superconducting gap, and this gap goes through so smoothly along TC, they may as well be the same gap. Okay? So we say this might be probably some sort of pairing above TC. Then the next thing here is that it's a doping dependent. As you know, a superconducting gap measures the bonding strength of the two electrons in a Cooper pair. And that gap should have been proportional to the transition temperature in the conventional wisdom. And you can see that, okay, as you go to more under the system, the gap gets bigger when TC goes down. Again, it's a disconnect. So there's a suspicion that you may have a system with a gap above TC. Okay. And then this will be a way to measure. Here I want to show you the results by Shuji Chen and Makoto Hashimoto in an overdoped system. So to give you a sense of it, here you see a spectra going from high temperature to low temperature. As you go from high temperature, you see a clear peak at the chemical potential. As you go to low temperature, somewhere between 130 Kelvin and 110 Kelvin, I hope you will see the single peak now split into two, and then the lower one become into the superconducting peak. Okay. I want to say that at the finite temperature, photon emission can see the state above the Fermi level because they are thermally populated. Okay. This behavior of a single quasi-particle peak split into two is exactly what you would have expected when you have a pairing, because the quasi-particle now turn into two Bogoliubov quasi-particle with the weighting of U squared and V squared. Okay. The only issue here now is this happened not at the superconducting transition temperature, above the superconducting transition temperature. So this hints that you have a situation of gap above Tc. Okay. Now, if this gap is superconductivity, one of the important features of superconductivity is the particle-hole symmetry. You could also have a density wave give you a gap, but it would not be particle-hole symmetric across the entire momentum space. Okay, and again, Schulte and Makoto set it out to do this experiment, and we measure the sort of the gap around the entire momentum space and try to differentiate whether it's a pairing or spin density wave. And you can see here the data, okay? The Tc is 77 Kelvin. If you can already see even at 85 Kelvin, it's fairly clear there's something happening at a chemical potential as a gapping behavior. Even at 95, it happens. So you can analyze this data over the sort of all the relevant momentum space. You can see that the upper branch and the lower branch are symmetric. Okay, so in sort of everywhere in K-space. So this, of course, is consistent with saying you have a gap, a particle-hole symmetric above Tc, and that's consistent with the picture of pairing above Tc. Of course, this is also something Professor Ornstein's group have been said in the same system long time ago, superconducting fluctuation above Tc. Now, I've shown you the data taken in overdoped regime. I want to show you this set of data, which bring out another dimension in the problem. Now, this is about 19% doping, and this about 18.5. This is the sort of 19.5. I hope on this side, spectra looks, this relatively narrow range of doping from 16 to 21. Spectra looks more or less the same, but I hope you see as I go to lower temperature, near the dashed line, which is the chemical potential, you see spectral weight gets suppressed, okay? And with the energy scale about 100 millivolt. So in other words, there's suppression of the spectral weight, and usually what it means is some sort of gapping. And because that's not very well defined, and usually you refer to this something called the pseudogap. Now let's look the other side. I hope you see it's very different. Nowhere there's a suppression of spectral weight at the dashed line, okay? And you can see that this is the one group of data, and this is another group of data. They just look very different, okay? Seem to be independent of the temperature. Now, if you go to even lower temperature, I hope you can see on this side, as you go to even lower temperature, there's a shoulder developed. And this develops above Tc, and then developing into the superconducting gap. On this side, which I have already explained, one peak split into two, as you would have expected in a pairing scenario. However, if you look at low temperature, they look very similar. Okay? This data looks extremely different if you look at the high temperature data, but at low temperature, it looks very, very similar. Okay? That's remarkable. You could have, disordered sample give you spectral look like rare spectrum, very broad, but we know that they will not suddenly turn into a very good sample with a sharp peak. And the fact this shoulder develops, you can see the shoulder above Tc is consistent with this guy splitting in this. From this, we will say, hey, you have a situation that there appear to be a pairing gap above TC, then there's another even higher energy scale in underdoped regime. That will be the sort of the picture. So what they were saying that, okay, you ask, then what happened to this sort of true thermodynamic peak in this way? Okay, what happening at the long range ordered? What the spectroscopy will tell you in this case? Okay, we know superconductivity within the framework of BCS. There are these four features: zero resistance, and diamagnetism, and a jump in the thermodynamics, and then there's spectroscopy. All this is seen, but really, what is the connection of the spectroscopy remains a question. For people who are familiar with both photoemission or STM or this kind of spectroscopy, the temperature-dependent experiments are very, very hard for precision measurement of that. And this being overcome, and what Schutte and Makoto have found is that if I would use, instead of density of state, just the spectral weight at the chemical potential, and use the stent as sort of spectator of the density of state, and then use the standard way to calculate the entropy of the system as a function of temperature, then you get an entropy curve look like this. Okay, and we know if you make a derivative of the entropy, then you see a jump. That is the photoemission data, and the black curve is the specific heat. So you can see, okay, it's really the weight of the chemical potential that gives you. And they were also able to measure that you can see that at the antinode, this jump is big, at the node is small. This behavior, you can model it with phase fluctuations. So all this is consistent with you have pairings about TC. Okay. So what I just told you is the physics of the whole doped system, and I just want to mention that in electron doped system, actually they're similar. Even in this innocent-looking insulating phase, there appear to be another gap along the antinode direction, and this gap, and for the theoretical work of Dang Hai, is fairly consistent with a pairing. But it's very interesting. Let me just point out that this gap actually has no node, even though it's a D wave. The reason is that this reconstructed Fermi surface, you already have taken into account of sign change. So if you sign change once more, you cancel the node. So all this is pointing to there's a lot of pairing which is not connected to the global superconductivity. I hope, so this will be the summary of, we got a D-wave pairing, and we say there's a very clear evidence of disconnect between pairing and TC. Looks like there's a lot of preformed superconductivity. This will be something we feel confident that there's enough evidence for it. This will be some, we can hold on to it. Okay. I also hope this will give you a sense of what this technique can give to you. Now let me move on to the part which is more speculative, okay, and just to stimulate discussion. So the remaining puzzle is actually interesting. We know a lot more about the superconducting state than its strange normal state. This is different from the typical Fermi liquid instability drive superconductivity. So when you have a situation like this, it turns out that it's very important. Many things did happen. The very important is what question you are asking. In particular, there's a phenomenon called a pseudogap. I think you probably hear a lot. At the cartoon level, what the pseudogap means is that, you know, the Fermi surface is a concept of how many fermions you have in the system. you should not stop in the middle of nowhere unless you have a peculiar topological property. Usually you don't. The pseudogap is essentially a way to say that the Fermi surface stopped in the middle of nowhere. And you can see here that's very generic. I mean, that's, you can see the sort of Fermi surface stop in the middle of nowhere. That's the puzzle and the general phenomenology of this problem. Okay. Now, what are the microscopic ingredients could possibly giving this and also link to superconductivity? So now let me explore that a little bit. Okay. So it's clear that one important microscopic ingredient has to be some sort of Coulomb repulsion or self-generated exchange interaction. Because we have a D-wave pairing that's most natural, and also I'm going to talk about, it turns out that the spin is very important to control dynamics, okay? And you also see so-called hotspot on the Fermi surface. So it turns out this will be important as an input to the discussion of the Hubbard model. The next question will be, is that sufficient? Okay. And this actually is the work we did with Bob when he was still at MIT. And that is a beautiful system, and this work by Barry Wells. And you can see that that is the theoretical prediction, and that's the measurement. Two things happen. One is you can see it reach a maximum halfway at half pi, half pi. Second is that the bandwidth is severely narrower than this. And it turns out that this bandwidth is completely controlled by the exchange interaction of the system. It's telling you how important the spin interaction in this system, and the J can be independently measured by neutron scattering. This works very well setting the scale. But there's a puzzle. You can see the data agrees with so-called the TJ model calculation very well along the zone diagonal direction, but near the zone phase does not agree. And this is related to the things which I formulated earlier as the pseudogap physics. Okay. The other evidence of exchange interaction is so-called hotspot in the Brillouin zone. And this was already there in Peter Armitage's thesis work. And you can see that it turns out that the Fermi surface is severely truncated at the intersection between the underlying Fermi surface and the anti-ferromagnetic zone. Okay. So now there's modern work on this. You see even the other side of the Brillouin zone. But nevertheless, telling you the magnetism played a very important role in this. And most recently, we also made progress in electron-doped system. It turns out this is very helpful to gain insight of at least a component of the pseudogap physics. And it turns out you can see there's a very large energy gap. Then there's also additional state inside the gap. For an insulator to see state inside the gap is nothing strange. But what is important is that, because impurity state can give you a gap, what is important is that this state actually is the one developing into superconducting state. And this is the work Zhi-Xun Li and Dong Hai pointed out that if you consider the orientational fluctuations, you can explain. So this, I won't go into the details. This is saying that the pseudogap physics has a component of the magnetism. Okay. Then the next question is that, okay, this is very important to have this vision, but is this sufficient? You know, the Hubbard model, there's a lot of work, numerical, there's no consensus, even to this day, for two-dimensional systems, because they're very difficult to solve. We know that in one dimension, it turns out you know the theoretical answer to the Hubbard model. In two-dimension, because if there's a disagreement between theory and the model, you don't know if the model itself is insufficient or the calculation of the model is not reliable, okay? So in one dimension, let me just say that there's a phenomenon called the spin charge separation. In other words, the picture I show you, this single band, but in a magnetic chain, it turns out it breaks into two branches of spin branch and the whole branch, and there's a continuous excitation. And that's what is being seen in so-called hold-on and spin-on. And you can, again, constrain the exchange by neutron scattering. And you can see it's the pretty satisfied description. This, again, to say that this sort of physics is necessary in the system. Then the same question will say, is that sufficient? Okay. It turns out the material world is such that this material cannot be doped. Being struggled for a long time, you cannot dope. Therefore, you cannot answer the question, what happens to the two holes doped into the system, okay? And with the molecular beam epitaxy, that's the work of Zhi-Xun when he was in the group, and it turns out you could stabilize the doped system. Here you see two sets of one-dimensional Fermi surface because the material has the domains. Okay, so this one-dimensional Fermi surface, there's another one-dimensional Fermi surface. He was able to dope the system up to 40%. Okay, and with that, you can now take a profile of the density and try to compare results of the Hubbard model calculation and try to quantitatively benchmark. And that's the experimental data, and this is the Hubbard model result. Okay. Most importantly, look at this shoulder feature. That's the so-called 3KF feature, which is the most sensitive to the interaction between two carrier, two doped holes. And with a lover's eye, you may say there's a tiny bit of a signal here, but it's clearly less than what is seen. So now if you say, okay, already taking into account on-site cooling interaction as in the Hubbard model, what about add one more term? The next term to add will be the next neighbor interaction. The next neighbor interaction, you can have positive term, doesn't seem to do much. Then if you do a negative term, it turns out if you add a next neighbor interaction or negative term of T, and you can see the profile agrees experiment pretty well, okay? So in other words, in the real material, there's one more attractive interaction which is now being accounted for in the single band Hubbard model, okay? What is also interesting is that once you add this one single parameter, you can explain the entire doping dependence. You can see this profile, this intensity decreases. So we feel that it capture the right kind of physics. So in the system we are talking about, there's additional attractive interaction in the problem. Of course, you can ask the question, what is the source of that attractive interaction? Okay, then most natural one will be the vision by Alex Muller to say that the natural that there will be electron-phonon interaction and in this problem. And as you can see that there's a pretty good evidence. That's the earlier work, pioneering work by Alessandro Lanzana. And you can see that if you do have a coupling, you will see an anomaly in the dispersion of the phonon frequency. And it's seen routinely now with good resolution. In other words, if you have a smooth curve, should have been linear in a small energy scale of the phonon. But the fact you see a change of the linear dispersion is telling you you have some sort of. So this is sort of routinely seen in this system. Another thing is also, I told you earlier, there's dispersion being completely controlled by the J. But this data has one more puzzle, namely the spectra at the maximum you should have seen a very sharp Lorentzian spectrum if that's a spin-only model. But the data always see a broadened Gaussian model. And that was the work by Carl Shen in his thesis, and we were able to figure out the Polaronic type of behavior here. Once you solve that, also solve a long-standing issue of what happened to the chemical potential in this problem. So there's, again, evidence that there's additional physics in the problem. Okay. So if I will take those put together, then the really question will be, what is the sort of, what about this some sort of combined effect of these two visions? Then you can ask, okay, usually the phonons are not very good for D waves. This is one of the remaining puzzles. But there are evidences that there are a lot of small Q phonons, in particular in this vision of poorly screened metal, you have a forward scattering. Then this raised the question, is the D waveness and the highness of TC exactly the same thing? Okay. Again, this is the momentum dependence of that. It turns out, certainly for this system, the strongest coupling one appear to have this so-called B1G mode of D-wave-like phonons, which will be cooperative. And also very interesting, that's the thesis work of He Yu. He was a postdoc here, also in Bob's group. And as you can see that in a very narrow range of doping, the superconducting gap goes from about 10 millivolts, that's sort of weak coupling BCS D wave, to 40 millivolts, a factor of 4 change. Okay? That could be a difference between low TC and high TC. That appear to be correlated with the involvement of this particular phonon. In other words, you could have the phonons enhance superconductivity, bring the number up a lot. We are also inspired by this experience of, as probably you know, it's another superconductor, iron selenium. Relatively speaking, it's a low TC material. But if you grow this material on an oxide surface, the TC goes up by a lot. It's a combination of doping and as well as decoupling with the interface phonons with a small q. And that's the work being done, the ideas coming from Danhai we can account for. So you can see that those things are working together. So I hope to give you a summary of, I hope the spectroscopy can tell us things like, D-wave pairing, disconnect between pairing and TC. So it's a reliable pairing thing. Then the puzzle is the pseudogap compressed normal state feature. We think both the magnetism as well as the additional phonon effect is important in the system. So the likely picture will be some sort of cooperative enhancement of the two and eventually give you the answer this question of how you can stabilize. Exactly what is being done to answer this question is to be settled, but we think the experiment suggests that those ingredients are necessary to consider, especially if you're talking about the highness of TC. And I've been reminded by this was a cartoon Bob was drawing, Bob Laughlin was drawing when I was giving a talk, and he gave it to me after the talk. He said, maybe that's what you're saying is some sort of amplifying effect of this. And if that's the case, then we have a possible way to forward. In other words, you could have a situation that the strong correlation amplify a small parameter of electron-phonon interaction. So you could have an effective, very strong coupling, but intrinsically not that strong interaction. Therefore, you won't have the structural instability. Okay. So then the question will be, would there be a case you could do test on that? Or is there a reason to believe this? It turns out you could. And this is a time-resolved experiment we can test and measure. In other words, I can see how much atoms move, and then you can see how much electron energy band move. And this is something called the deformation potential. So in time domain, you can achieve a precision not possible any other way. So this is a quantity. You can make a direct measurement of that. And I will just say that we measure both the lattice dynamics as well as the vibration of the photoemission spectra. When you put them together, then you discover that that's amount of lattice being moving, that's less than a picometer, and that's the amount of the energy level shift. And we can put that. Theoretically, we know that by considering electron interaction or not, you can have a very different answer. Dynamic mean field theory is cooling you into taking into account, and you can see the very different value. But you need have a precision with the error bar small enough to tell the difference. Now the experiment allows us to say that indeed this was the more correct answer. This is sort of a evidence, at least in this strongly correlated systems, correlation can really enhance the electron-photon coupling by order of magnitude. So I hope to end this by saying that we start out by a vision that try to tune up the parameters and to give high TC. And we know that, and start out with nickel didn't quite work, and the cuprate was discovered. We also know that there's a challenge of structural instability. Maybe the strong correlation can actually provide a possible way to end up in a situation you can achieve your goal, but without the detriment come from that necessary coupling. So let me end this by thanking the funding agency. So I'll be happy to take questions. Thank you very much.
Questions?
The exterior group has also done beautiful work on the iron-based superconductors.
Yeah.
How do you see those fitting in, and do they give any insights in either the nickel or the copper?
I don't feel myself had a very coherent picture for the iron-based superconductors. There appear to be the matter more of a from the limit of matter physics. Fermi surface scattering will be as important. But even there, I would say the system with the highest TC still involves light atom. Those are the 1-1-1-1 phase with oxygen. So I don't think I feel we've done enough to say. But I do have cases where when you do involve those, like the monolayer case, if you do involve two channels in a favorable condition, you get extreme numbers. Please.
So at least conventionally, I think of phase transition as perhaps a spontaneous symmetry. And in the case of superconductivity, there is U1 Morgan symmetry, and the gap function is the order parameter that represents that gap of phase. So with this fluctuating superconductivity, we have paired above TC. Is that symmetry still broken?
I would say this is something you probably want to ask for for a series of that. My understanding will be that symmetry will be broken at the true superconducting phase. Otherwise, it's not. Yeah.
Any more questions? So, Zhi-Xun, you have spent a long time perfecting angle resolved photo emission. In your dream, what other advancements you can make so that it will eventually lead to deeper insights into the copper oxide problem?
Maybe instead of telling you what's my dream of hoping, maybe I can explain what we're doing. Okay, we try to do spin resolved experiment. That is a work pioneered by Alessandra here, also Zahi, and we are adapting that, and we get to a point that we feel we can learn a lot. Everything I show you here is about the energy spectrum, the Venn diagram of that. But in condensed matter, as we've been reminded by the recent advance of topological insulator, the information of the eigenfunction or the wave function is also very important. And by doing spin-resolved experiment, you actually can learn information about the wave function, which I think is important. For example, we feel we are making good progress on this puzzle why you don't see the gap in the magnetic topological insulators by figuring out the wave functions. That will be one of the things we're doing. The other thing will be just small spot, okay? Therefore, you can look at this more samples and yeah. So I would see this technique is still on a very rapid development. And again, the small spot experiment clearly was pioneered by Eli Lotenberg and his colleagues here at Berkeley. Yeah. I should also say I've shown you a glimpse of the time-resolved experiment. You know, see atoms moving and tracking the electrons. Honestly, I myself didn't dream about that level of precision. We know that the error bar was too big to test this important. I didn't realize that level of precision you can achieve. The time domain could achieve a precision that is impossible to with the frequency domain. For example, you can know exactly which phonon you're coupled to by looking at the oscillation. So that will be another thing. Yes, please.
Yeah, I have a generic question. How do you safeguard against the effect of inhomogeneity when you're making your RPES measurements, right? I mean, you have these materials where you're throwing in dopants and they're all over the places. Microscopically, a very disordered system.
Absolutely. I mean, you know, there's a lot of experiments, a lot of reason to believe that there's a lot of inhomogeneities of that. But despite of that, a lot of the general trends, you can still gain insight. I've shown you one set of data, okay? And you see to the right-hand side with the 19.5% doping, to the left-hand side with 18.5% doping. They're really very different from that, okay? So there are inhomogeneities, but there's still a lot of things you can gain. Yeah. Sure. We, like all techniques, we have our limits, but really the question will be to what extent you can draw information based on that limit.
Any other? Okay, not. Let's thank Zhi-Xun for